I mean, we can discuss all the things over using my small iPad. I hope everything would work fine. So, can you see my screen? Is it visible?
Yes, ma'am.
Okay, very good. Just a minute. Okay, so is there any question from last class? Any question? No question. Okay. And so, okay, if you don't have any, right, please go ahead.
So,
Yeah.
is the kernel stack defined at the time of the initialization of a process, or
Right.
is
So
it,
unless
or
we
is it
don't have a
initialized at the time of the first interrupt or first system call? Because, I got this question because the kernel has like a finite memory. So,
hmm
is
Right,
there?
right. So that's a good question. So it's a design decision basically. So one can define when the process is created, right? At that time, one can define it. And another option is, as you are mentioning, when we need it at that moment, we can create it. So these are the only two options. Other than that, I mean, I don't know any other options, right? So, but there is always some, I mean, trade-off. So if you want to define it earlier, so at the time of the when you are going to create the process, then there is one benefit. So you don't have to waste time when that will be needed. But there is one disadvantage also. It might not be needed at all, right? Throughout the process, you might not need the kernel stack, right? You might not be trapped. So in that case, it is disadvantage. Okay, I am so sorry. I think there is some sound going on. Okay, so yeah, does it answer your question? Who asked the question? Maybe that would be good. Okay, Hetvi, right? Good. It was a good question. Any other question? Do you guys have? Okay, good that you had at least some question. Now let's see in more detail scheduling. So in last class, what we discussed is about something like this. We had context switches, right? And we saw the low level mechanism of context switch, right? But we left out this question. Let's say context switch happen. Now we know that it might not happen that the operating system will give the control to the same process, right? So there are several processes who are ready. Among them, it might decide some of the process. I mean, particular one process it can decide. Now the question is which process it should schedule, right? So that policy we are going to learn in today's discussion. Okay. Okay. Right. So is the motivation clear? So that's the objective of today's lecture. Okay. So we'll learn some scheduling policy, and of course, so again, so what is the scheduling? I mean, so what the scheduler is supposed to do. So when context switch happen, it should schedule CPU burst of a process, right? What is and what is CPU burst? So by CPU burst, we actually want to refer a continuous stretch of a process used by CPU. Okay, so that I mean that need to be used by CPU. That we are referring as a CPU burst. So, for example, I might have a process which actually it's interactive process. It's not that let's say the process is running from 50 millisecond, but it's not that whole 50 millisecond is dedicated to CPU. Some of the time is actually maybe for I/O purpose. So I'll not consider that I/O time in my CPU burst. Okay, so continuous stretch of a process which is needed by CPU. That time I will be referring as CPU burst. So, for example, if I have a process that might have several CPU bursts, right? Okay, good. So now, if you want to construct or build some policy, so there should be some. So it's not that we have only one policy, right? There might be several policy. Now you need to compare the performance of those policies. So there should be some metric, right? So we need to understand what are the metric that a scheduler should consider, right? So let us see those metrics. So of course, first metric or first parameter of comparison for different policy is utilization of CPU. Okay, so I mean, of course, you want to maximize the utilization of the CPU, right? Fraction of the time CPU is used, that you want to maximize, right? So it's one good parameter to judge. If I have several policies, that's one parameter to judge which policy is performing better with respect to utilization of CPU. Similarly, there is another important parameter which is known as turnaround time, right? So what is turnaround time? So it's actually the name, as the name suggests. So for example, it's actually basically, let's say I have a process which came at time at 12 o'clock it came, and when the job was finished, then it was 1 p.m. as for some examples. So turnaround time is basically the time when it was completed minus the time when it came. So it's for example the example which I gave, for it the turnaround time is 1 hour. Okay, so you want to minimize average turnaround time. So let's say I have n many processes running in my system. Now I'd be calculating. So using my policy, I'll see. I mean, what is the average turnaround time? Okay, and so you want to compare with respect to turnaround time. What is the average turnaround time for which policy it is minimum, right? So that's another parameter to judge. And third parameter is basically response time. Response time means, let's say I have submitted my job, right, at 12 o'clock, and it got scheduled at 12:30. So 30 minutes, basically, that is the response time, right? So of course, this parameter also you should minimize, right? So these are the main three parameters to judge. So there is another parameter which is basically subjective. Fairness, right? Means all process must be treated equally. So we should not be biased on some process, and right. So that fairness should be there. So if you remember, when we discussed, in the first class itself. So when we did not have operating system as a system, right? When human beings were there responsible to schedule jobs or operate or maybe play the role of operator, right? So there basically you can't think about fairness, because human beings are, they are very prone to be some bias, right? So since we have system, right, means that some policy we are going to build. So with respect to the policy, it should be the case that all process must be treated equally. There should not be some biased or something like that. Okay, and of course another important thing is basically of course you want to minimize overhead. What is the meaning of overhead? For example, how much extra work you are going to do, right? Of course we need to give CPU time for each job, right? They should be run in your system, right? But in order to maintain your policy, right, there should be always some overhead. Some certain kind of overhead should be there, and we should minimize that overhead. So these are the some of the scheduling metric, and so you understood. So there are so many parameters which you want to optimize. So those of you know already optimization. So it's actually multi-objective optimization function, right? So it's very difficult to get one scheduler which will perform with respect to all these parameters very. There is no so-called scheduler. Will not be. It's very difficult to get one scheduler which will perform with respect to all the parameters are the best. Okay. So now the question is, of course, you should have some scheduler for your machine, all right? You need to design something, and you may choose some of the parameter depending upon your choice. Okay, and when you are going to design your scheduler, so basically you need to understand what is the workload of the environment. Okay, in which kind of environment we are going to work on. So, okay, to start with, we are not going to assume something very, what should I say, realistic workload assumption. I'm not going to make. First, we are trying to give you some assumptions which are very simplistic in nature. And if you assume that that your workload is some kind of thing, which satisfies these assumptions, then the life would be easier for you. So let's see what are those assumptions. Okay, so the first assumption is basically we are assuming that each job runs for the same amount of time. Okay, it's a very basic and unrealistic assumption, I understand, but let's assume this. And again, we are assuming that each job arrives at same time. Okay, and they are only CPU oriented job. It's not that they are performing any IO. So there is no IO in these jobs. So jobs means basically process. We are referring jobs by process. Okay, and the runtime of each job that is basically known. Okay, which is also very much unrealistic assumption. In fact, all these assumptions are unrealistic. But let's say that we have jobs which satisfy all these assumptions. Okay. Now the question is, if you have this kind of assumptions, can you tell me? Can you give me some algorithm or maybe policy? Algorithm means here policy for the scheduler. Can you tell me some policy for the scheduler? Any answer? So it means you want to schedule the job, right, in your machine. So in which way you should schedule the job? That is the question. So there could be several algorithms, right, which you can think about. Just give me, I mean, not just guess what should be your algorithm or policy in this case. No answer? Yes.
Maybe like
Uh-huh.
schedule the job with like the minimum lines of code first, because the probability of that running faster is
Right. So shortest job fast you are talking about, right? Okay,
yeah.
good. That's right. That's one good option. Any other option? Right. Any other choice? So that's actually one good option, I'd say.
We can we like
Uh-huh.
formulate an optimization problem dependent on various parameters of the processes like size
Huh.
and
Right.
output
Ah.
arguments, and then solve it.
Mm-hmm. Yes, that's a good question actually. Since we are actually theoretical computer scientists, so we always do that. And to answer your questions, this scheduling problem is still a active field of research. Okay, so as I mentioned already, it's optimization problem, right? So it is actually interested to theoretical computer science. So operating system is not theoretical computer science; it's a system subject. Okay, and yes. I was disconnected. Hi, can you hear me? Hetvi, can you
Yes,
hear
ma'am.
me? Yes, okay. Sorry for the interruption. I was disconnected basically. Okay. Right. So, right, that's a good question, Hetvi. So, we can actually formulate this problem and try to solve in theoretical sense. Acha, just a minute. So, I am adding my desktop. I think now the power cut is, there should not be any power cut now. I hope so. Okay, right. To answer your question, yes, it's an active field of research. This scheduling problem, it's people are still actually working on. And if you have some, as I mentioned already, if you have some flavor on optimization, multi-objective optimization is really hard. Computationally, it's a hard problem, right? So you can't expect to achieve one algorithm or policy which will give you the optimum answer fitting all these optimization parameter. Okay, so if you are interested, you can have a look at this. Just search scheduling algorithm. Okay, you'll see several papers, and maybe in 2021 you'll find some. Okay, so in fact, in theoretical computer science, we study scheduling in the online setup and all. And these problems are already NP-hard problem with respect to different optimization. If you consider the different optimization parameter. Okay. So one can of course formulate that as optimization problem. It's optimization problem only. Okay. Okay. So yes. So as I asked you to guess some, I mean some sort of simple algorithm, right? H3 actually gave one answer. For example, shortest job fast, right? Any other answer? Any other algorithm which you know? Okay, so here is one, I mean, easy to answer, easy to formulate one algorithm or policy. Let's say fast come, fast serve. It's fair algorithm, right? Who is the whatever will fast come. I mean, the job which will fast come will give that. I mean, as in the CPU, right? Okay, that is one simple thing. So can you tell me which kind of problem we might face if we just implement fast come, fast serve algorithm, even in our simplistic assumption? Means if we just have, let's say, the assumption which we made earlier. So what was the assumptions? Assumptions were this thing, right? These are my assumptions. So is there any problem with fast come, fast serve with respect to all these assumptions? Is there any problem? Will it, so how with respect to response time, how it is? Is it a good algorithm? Fast come, fast serve? Is it a good algorithm? No answer? Hethi? Yes. Please go ahead.
I'm confused. Like, if we assume all jobs arrive at the same time, then how do we apply first come, first serve?
Right. That's a good question. That was I also I've been thinking that someone should raise this question. Good. So basically, yeah. So we assume that all jobs are coming at the same time. But since this is a system, right? So there should be some queue. You should actually, you can't say that all of them you got simultaneously. Even they come simultaneously. Let's say one of the job was actually taken by the system for the first, right? So there should be some first, second. Maybe it's a very negligible amount of time they came almost simultaneously. Okay. So that's a good question. I mean, for example, let's say I have 10 people, right? All of them went to the ticket counter same time, but they should, someone should be fast, right? So that fast is this one. That's a good question. Okay. Okay. So yeah. So it's a matter of how the system is taking them fast. All the jobs were all of them arrived almost simultaneously. Okay. But there is fraction of moment difference, let's say. Okay. According to how the system is taking them. So that with respect to that, we are saying that fast come, fast serve. Yeah. Okay, so this simple strategy will work well, but let's say I have, you can see this is basically one picture. If we have 3 jobs, then basically first how they are actually scheduled by the CPU, right, with respect to time. So this fast come, fast serve, does it have some problem, or it will work very nicely? Does it have some problem? So with respect to response time, how it behaves, or with respect to turnaround time, how it behaves. Okay, so you can't judge this unless we have another algorithm, right? Okay, so now let's consider this with respect to, okay, we'll consider how this algorithm is uh, behaves. Okay, so let's see what is Hetfi's algorithm, right? So Hetfi suggested another algorithm or policy, which is actually shortest job fast, right? So here you have the, as she suggested, I mean, you have several jobs, all of them, let's say, came at the same time. Now you are going to choose the shortest one first, right? So you can see, now can you compare? So you have understood at least 2 algorithms, right? Fast come, fast serve, and shortest job fast. So now can you compare with respect to, let's say, turnaround time, average turnaround time, which one would be better? Or with respect to, let's say, response time, which one would be better among these 2? Okay, can you think about this? because these parameters are only for comparison purpose, right? You can compare with respect to these parameters. So which one is better among the shortest job first and the first come first serve? Any answer? No answer. No. So do you understand what is the turnaround time and what is response time of, I mean, of some scheduler with respect to some jobs, right? You have a set of jobs, right? So what do you think? Turnaround time would be better for which of these algorithm? Okay, so now let's see example. So let's see if uh, this is your job, let's say ABC. So A, let's say A came first, then B, then C, right? So with respect to these three jobs, right? So what is the turnaround time, average turnaround time for first come first serve? And what is the turnaround time of shortest job first?
40 seconds.
40 seconds for first come first serve.
No, shortest.
Shortest job. Okay. Turnaround time is basically so right, for B you have 10, then C you have 20, then this is okay. So you are saying this is okay. You can calculate it. I am not asking you the exact answer, but I am asking you. So for which one it is better with respect to turnaround time? So if it is scheduled by shortest job first, the scheduling would be as given in this picture, right? And if it is if it is first come first serve, A came first, so A should be scheduled first, right? So first, the picture would look like this, just opposite, right? So you would have maybe this. First, this is the big job A, then small b, then small c, right? So what is the, with respect to turnaround time, you can see, right? With respect to turnaround time, average turnaround time, shortest job first performs better, right? Or not? Hmm?
It is lesser.
Lesser means? So you
Like,
want to minimize.
yeah, shortest job first will minimize it, right?
Right, so that's what I am saying. Yeah, shortest job fast will minimize. So, and the objective is to minimize turnaround time. So, with respect to turnaround time, shortest job fast performs better, right, than the fast come fast serve. Am I right?
So, but haven't we assumed that each job runs for the same amount of time?
Right. So, okay, very
So,
good.
but,
Uh,
yeah.
right. So that's a good thing, good question which you have asked. Okay, so we had this primary assumptions, right? Okay, I did not mention this. So we are going to lift out all these assumptions one by one, since these assumptions are not realistic. Okay, we made these assumptions at the first time. Okay, because if you have this simplistic assumption, having the policy would be better. So that's why having these assumptions, we constructed, or we just got one algorithm which is known as, let's say, first come first serve, right? Okay, so we are going to lift one by one all these assumptions. For example, now we are lifting the assumption that all jobs are of same length. Okay, this assumption is now lifted, let's say. So then you can see for first come first serve, I mean, it is not going to perform better, right? We are lifting, let's say, this first assumption which we made, that all jobs are running for the same amount of time. Sorry, that was the third assumption, I think. All jobs uses only, no, each job runs for, right. So there's a first assumption, right? We are going to lifting this assumption. Okay. Okay, if you lift that assumption, now you can see shortest job performs better. In fact, the first come first serve, or FIFO, it actually has this convoy effect. Means, let's say I have a big job, right, which actually came fast, right? So, and your scheduler doesn't know about it, how much time it is going to take it or something like that. So it's a big job. In fact, you ignore that fact, and you just get it scheduled in your machine, right? So all other smaller jobs are going to be starving for this, right, for a long time, right? So it is known as convoy effect, and maybe you can see, you might have seen this effect when you might have, I mean, you might be going for marketing and all, right? So for example, let's say some supermarket you went, right? So you must have seen that, okay, some family person has so much items to bought, and so if he is actually at the front of your of you, and you have, let's say, 2 or 3 items which you bought, so now in the billing counter you need to spend lot of time, right? So that's why FIFO is not that great, right? And you might have seen that to avoid this convoy effect in the market, I mean, most of the supermarket, they have priority queue, right? Priority billing counter, right? So where they just permit all the customer having maybe 2 3 items, or maybe at max 5 items, right? Okay, so another important thing. So these algorithms, whatever we are discussing, this shortest job fast or FIFO, these algorithms were actually there even before computer came, right? For example, FIFO is very natural algorithm, fast come fast up, right? So these algorithms were basically used by operation research community earlier. Okay, so from them, operating system guys, they actually borrowed all those algorithms in the early days of computer. Okay, so FIFO, shortest job fast, those were already known. It's not that, of course, I think all of you must be knowing these are actually very natural algorithm, right, or natural policy. Okay, now the next question is, can you give me some example where shortest job fast will also performs very poorly? Okay, you don't need to compare with respect to fast come fast serve, but shortest job fast itself will perform very poorly. Can you give me some example? Can you construct some example? Example means, of course, you need to construct some process with some time, right? When they are coming, and what is the amount of time they need to work, right? And according to your SGF algorithm, how you are going to schedule them. Okay. Now let us consider. I mean, if you want to construct that thing, so let us again lift another assumption. Okay, I'm just removing another assumption. We said that all jobs arrived at the same time. Let us remove that assumption. Okay. If all the jobs are arriving at the same time, right? Right, then maybe shortest job fast is actually performing very nicely. So now let us remove the assumption that all jobs arrive at the same time. Okay. So now can you construct one example where shortest job fast will actually perform very poorly? Can you give me one example? Is the question clear to you? Okay, I should not show it. Is the question clear to you? Is that Hethi, are you going to speak? Yes.
Yeah, then
Yeah.
it can be something like
Hmm.
first you
Hmm.
give the largest process and then wait for 1 second and then give the second largest process so that the largest process already starts.
Right. Okay. So you said, okay, since this is okay, right. So the picture will be something like this, as Hethi is saying. So I have since the job object, I mean, jobs can come at any time, right? That restriction we have removed, that all of them are coming at the same time. So it might happen that the current job, whatever you have at your hand, so you need to schedule that job. That job might be very big, right? And you have scheduled. Then after it got just scheduled, maybe within a fraction of moment later, right, one small job came. Then the shortest job fast will actually behave similar to fast come fast serve only, right? So this would be the scenario then again. So big job got stuck. I mean, your CPU is actually now occupied by that, and all other small jobs are actually waiting for that big job to be finished, right? Okay, now can you come up with some idea or policy which will actually avoid such situation? Okay.
Ma'am,
Can
I
you
have a
modify?
question here. Are we not considering the interrupt time?
Okay, right. So, good question. So, okay, very good. So, what do you mean by interrupt time?
What
Okay.
you mentioned in the last lecture, like that
Ah, ah,
time
okay.
and the non-cooperation thing where like
Right,
the
right.
system is taken over
Okay.
by the OS and
Right,
you
right.
schedule.
So good question. So yes, so here basically, right. That's the thing. I mean, if you want to come out of the such situation, you need to introduce interrupt, right? You need to actually, your system should be preemptive system, right? Scheduler should preempt. Means if you see that some job has actually come and its time, I mean, the running time is very less compared to the job which is actually running. So you see what is the remaining time there, right? So you introduce preemptive for this purpose, right? So that's another, I mean, that's another motivation to introduce preemptiveness in your system. Okay, so right. So if you want to introduce that preemptiveness in your picture, then you can actually update your SJF, shortest job first, right? So which will actually consider the shortest remaining job first. Okay, so, or maybe the term is shortest time to completion fast. Okay, it's exactly same as SJF, just you have introduced preemptiveness, right? You just see if some job comes, right? So interrupt would be there. Then you see the completion time, whatever the remaining completion times are there with respect to all the ready jobs, right? You see whatever the minimum completion time is there for that job. You just pick it and schedule it. Okay. Okay, good. So with that, the picture would be something like this, right? Now, that job, big job A, it is actually preempted, right? And it got scheduled here. Other smaller job will be executed first. Okay. Okay, very good. Good. So now, so you see another other examples basically. This is 5 jobs, right? If they are, if you maintain the policy FIFO, then basically they will behave like this, right? The bigger job will stack over here, other smaller jobs will be waiting, right? And with respect to shortest job fast or maybe shortest completion time fast, if you modify it, then it will look like this, right? So turnaround time is less, and also response time, with respect to response time also, FIFO, I mean STCF is performing better than FIFO, right? Okay, very good. Okay, I mean if you compare with respect to FIFO and SJF, then STCF or SJF, whatever, they are performing, STCF is better than FIFO, right? Um, okay, but here again, with respect to response time, both of them are relatively slow, I would say, right? Because if you see here, this second job, third job, fourth job, they all had to wait for a long time, right? So what is the response time? If you remember, the response time is the time when the job came fast and when the job was scheduled fast. That gap is basically response time, right? So you want to minimize that response time. So with respect to, so we did not care about response time when we designed this STCF or FIFO, right? So now if you want to introduce this response time, means if you want to build your policy so that it is actually, it performs very nicely with respect to this parameter response time, then what can you think about? Which type of algorithm or policy? Can you think about some policy which would perform better than STCF with respect to response time? Okay, so what can you think? What do you think? The natural thinking. If you want to just forget about turnaround time and all, okay. Let's say we want to improve response time in your system. Okay, so what should be your policy? So can you think about something, some policy? It's very obvious, no? So if you want to, I mean, if you want to improve the response time, it's good to schedule all of the job as early as possible, right? So in other sense, I would, let's say I would have some small fraction of time given to all of the jobs, right, in round robin fashion. So let's say I'll schedule the first job, maybe whatever you have available at your hand, and give it very small amount of time or some certain amount of time interval, right? Then you schedule the next job, right? Again, give it that same amount of time. Okay, so this is called round robin. If you just implement the round robin scheduling algorithm, then basically it will improve your responsive time of your system. Okay, I hope you have understood. The picture is something like this. So you have, let's say, the same job A B C D, whatever we had. Sorry, three jobs A B C. So, and the turnaround, so the interval which you have, or time slice which you have considered, this is, let's say, this interval. So you just, after giving that amount of time to a specific job, you just preempt that job, okay, context switch that job from another to some other job in your queue, okay. And you do this in round robin fashion, right? So you can see after ABC, you again A got chance, right? So if some job is finished, then you don't need to give it again. But if it is not finished, so they will come in the round robin fashion. Okay, this is also very natural algorithm, right? So average, with respect to average response time, this algorithm works very nicely. Okay. So basically, here the main thing is you need to consider that time slice which you are going to give, right? So that amount, which amount you are going to give for each job, that is a design decision, right? So you can see, I mean, can you see that if you are going to give very small amount of time slice for each job, then you need to do many more context switch, right? And that context switch is a overhead, right? So if you want to lower down your overload or overhead, right? So then basically that time slice should be bigger in size, right? On the other hand, if you want to minimize your response time, then the time slice should be smaller. So there is always a trade-off, and this is always design decision, which one you should take. Okay. So right. So for example, if the time slice is too long, then basically it or maybe let's say infinite, then the picture is similar to what? Can you tell me? It's similar to first in first serve, right? First in first out, right? And if the time quantum is very short, right? And let's say just one instruction, right? So then basically it's too much overhead. You are wasting your overhead. I mean, if you are wasting your resource, maybe the CPU time is also wasted in that sense. So it's CPU utilization, right? So that is actually, fraction is actually now that utilization or usage of CPU is less. Okay. Okay. So right. So this is basically, as I mentioned already, shorter time slice means better response, but context switch will dominate, right? And longer time slice means, okay, so amortize cost for this switching is less. That is good thing, but with respect to response time, it performs very poor. Okay, and there is always a trade-off, right? And this is the trade-off of the designer, so or system designer. They need to decide what should be the time slice. Okay, with respect to that, your system will perform better. That they need to design before giving that time slice. Okay. Okay. Good. Okay. Now I have one question for you. Let's say uh, zero cost time slice, right? Means, so if you are context switching, right? So you are spending some amount of overhead for that, right? So let's assume that that overhead is basically empty, nil, right? So that is zero, let's say. So if that is the thing, that overhead is actually not there. Now, is it that round robin will always perform better than FIFO? So that's a big question. So do you understand my question? So my question was something like this. So you have understood that if you are going to implement round robin, there is a overhead, right? That overhead is basically the context switch overhead. If the time slice is very small, it's going to give you a huge overhead. So assume that this overhead is actually 0, even if you are going to implement round robin with any time slice. Let's assume that. Okay, so now the question is, if that is the case, then is your round robin algorithm will perform always better than FIFO? That is the question. Can you give some example, maybe where round robin performs maybe poor compared to FIFO? Can you give some example? I hope the question makes sense to you. Any answer? Any answer? No answer. Think about it. Okay, so here is the answer. So you see this example. Okay, so here basically it is according to round robin fashion. We have scheduled we have 5 jobs, right? And this is the time slice, let's say this length. So 5 jobs got scheduled, right, one after another. And so at this moment, this job was finished, first job, right? At this moment, second job finished, this, right? Now you see the same job, 5 jobs. If you are going to schedule them with respect to FIFO, then this first job will be actually completed here, second job here, there, 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 right? Now if you can see with respect to turnaround time, right? So what is the average turnaround time for round robin and FIFO? Can you compare it? So if it's from the picture itself, it is obvious that average turnaround time of round robin would be much more, right, compared to FIFO, right? So with respect to turnaround time for this particular example, FIFO works better than round robin, right? So though we actually it's counterintuitive that you might think that okay round robin will be better performer, but it is not. Okay, with respect to, in other words, with respect to turnaround time, round robin is not performing good. Okay, so in fact FIFO is better. If you compare with FIFO, that will be also better compared to round robin. Okay. So in other words, round robin is good. It's a fair algorithm, right? So it is giving all of the jobs fair amount of time slice, right? So in that respect, it's fair. And of course, with respect to response time, also it is good. Its performance is good. But with respect to turnaround time, it performs very poorly. Okay. So in other words, if you see all these algorithms in the picture, I mean, so far we have seen 3 policies, right? So with respect to turnaround time, shortest STCF, okay, shortest completion time fast, that algorithm performs better than the FIFO, right? And I think that's the best option so far with respect to average turnaround time. And if you see the responsiveness, then round robin is the better choice. And there is no such answer that okay, this is the algorithm which performs with respect to all these parameters. Okay, at least for these 3 algorithms. Okay, now let us see. So far actually, so we have lifted many of the assumptions, right, which we started with. If you remember the assumptions which we had, all the unrealistic assumptions. So far we removed these 2 assumptions. But yeah, so most important assumptions which we have is these 2, right? So we were assuming that all the jobs are actually CPU oriented job, right? Now let us remove these assumptions. So in other words, we might have some jobs which are actually performing IO, right? Okay, if that is the picture, now the question is how you are going to schedule them. Okay, so for example, let's say how you are going to if let's say I have many jobs, right, and some of them are actually performing IOs. In fact, all of the jobs are going to perform IO. There is no job there should not be, in the ideal situation, there should not be some job which is not performing any IO, right? Unless and until you have some infinite for loop or something like that, just unnecessary, right? So, for example, if you don't have IO, so what it is supposed to do? So, with this, if you don't take input, then your algorithm is actually giving you all the time. If you run that the same algorithm all the time, it will give you the same answer, right? And where you are writing that, if you are not going to do some IO, right? So who cares about your algorithm if you don't perform IO? So that's why we should actually introduce IO into the picture, right? Okay, now the question is, if you have IO, and let's say again we have fast in, fast out, right? Fast job came fast, and you are going to schedule those jobs according to your policies. Now let's see how they behave. Okay, with respect to some example, of course. Let's say I have two jobs, A and B. So A is basically, it performs IO operations. Okay, it runs for 10 milliseconds, then it is basically asking for IO, right? Interactive job. And the other job B, for the time being, let's say it is a CPU oriented job. Okay, it is just doing some computation. Okay, and if each of the IO, it will take 10 milliseconds also. Okay, so if you are going to schedule the job A fast, okay, in the picture, then the picture looks like this. And if it is non-preemptive scheduling, right, and it's a FIFO, right, the picture would look like this. So you can see job A, it was on CPU. Then at this moment, it actually it went to do some IO, right? Then it came back, and again after this moment it went for IO, right? So all these moments actually the CPU was idle, right? Okay, so this should not be the ideal case, right? So since you already know the context switching and all, right? So in fact, this CPU time we can actually utilize, right, by giving the chance to run the other process, right? So the better choice would be something like this. Since you have already learned context switching, right? So we should have something like this. B should be scheduled in between, right? When the process A went to do some IO operation, right? So this should be the thing when you are going to incorporate IO. Okay, so I hope you have understood all these things. So far, what we have considered is basically, I mean, if you go back to the assumptions, we have lifted 3 assumptions, but the 4th assumption it is still there. The runtime of each job, we assume that it is known, right? So it's unrealistic assumption. Okay. So now the question is how you are going to remove this assumption, right? If you are going to remove this assumption, then what should be your algorithm? Okay.
No,
I hope you have
I
understood. Right.
question related to IO. So is the time is like the order of magnitude of the time in which it takes to perform the input output operation? How is this helpful if like the interrupt time and this time are of the same order?
I didn't understand. Yes, say that once again. So you are saying that IO time, whatever it is, let's say for this example,
If
the job.
if that time is like is of the order of the time it takes to issue an interrupt. So like if it takes 5 milliseconds to issue an interrupt and IO time is also similar to that,
Okay.
then how is this like
Okay.
does it help in those cases?
Acha, okay. So you want to say this time, whatever this time, let's say it's very few amount of time. That's what you are saying. Is it
Yeah,
something like that?
yeah,
Okay.
because IO should be very fast, right? So
Right. No, IO actually it is not fast. So so CPU is actually IO is not fast. Yeah. So you will learn when you will learn IO, you will see actually the if you are performing IO, right? So it's actually time consuming job. For example, let's say even if you are going to give some input from keyboard, then to of course it is slow. And even if it is going to read from some file, or if it is going to write something to some file, okay, in hard disk or somewhere, that time actually it's a huge time compared to the CPU time. Okay, because if you want to perform something, CPU is very fast compared to IO. Within that IO time, you can actually utilize your CPU. Otherwise, that CPU time will be wasted. Okay, so that's the reason. Okay, so that time is not going to be very small. So if you are thinking that okay, yeah, I am going to click very fast, going to give some response fast, that time would be very large compared to CPU, because CPU actually nowadays you can see how many instruction it can perform in your CPU. If you see the hearts of your machine, no? So you will see how many instruction it can perform. Okay, so it's very fast. So IO time is actually very high. So it's ideal. I mean, we should actually utilize that time, that IO time. Otherwise, it will be a wastage of the CPU time. It's a wastage of resource.
Okay, got it. Yeah, I did
You
not
got
know.
it?
Yeah.
Okay, okay. Thank you. Do you have any other questions?
No,
Any
no,
other question? Okay.
no.
No, right? Okay, I hope you have understood this. So far we have actually considered, uh, so far we have only considered uh, that all the jobs are not coming at some time, right? That in the previous assumption, whatever we had, that we actually lifted, right? And they don't have same amount of time, CPU time, and they are also doing IO. But we take it for granted that we know the amount of time, whatever we have for each job. I mean, as if we know a priori the amount of time the job is going to occupy the CPU, right? Which is very unrealistic assumption, right? The last assumption, which we could not lift it, right? Now the question is, if you are going to remove that assumption, what should be your algorithm? So here there is no concept of shortest job first, right? So okay, round robin you can always apply, right? But you see the problem with round robin is it behaves very poorly with respect to turnaround time, right? So we want to have some policy which performs very good with respect to response time, and it will also perform good with respect to turnaround time, and it should be fair, right? There should not be any starvation, right? So starvation means, for example, some small job is waiting for a long time, let's say for the CPU, right? So that should not be there. So what should be the algorithm or policy, right? So basically, here is the answer. We have another policy which is known as, actually this is widely implemented. This is widely implemented in many systems, which is known as multi-level feedback queue. Okay, this is another policy, and the person who invented this policy, his name is Colorado, I think. If I am not, I mean, I am very poor at remembering name. So that person actually he got Turing Award for this. Okay, this after inventing this multi-level feedback queue, because this is very much useful. You will see. So what is the main the goal? If you understood the scheduler so far, so your scheduler should be very good with respect to this parameter. Responsiveness should be very low, right? There should be low overhead, and it should be starvation free. So we'll see in more detail what do we mean by starvation, and it should be fair, right? And so far we have seen all the algorithms, means three algorithms only we saw. So none of them are perfect at any of them, right? It's not that, I mean, we don't have anyone which is perfect at all of them, right? Okay, so now the question is, how would you implement such policy, right? So if you want to implement such policy, because you don't know the size of a job, right? Whether the job is CPU oriented or IO oriented, that information you don't have. So what the multi-level feedback queue will do, it's a scheduler which will learn from the past, okay? And that information means the according to the behavior whatever your job had in the past, according to that it will predict its policy. Okay, means what should I do with respect to that job, because in the past that job actually behaved, let's say it was a CPU oriented job. After observing this, the scheduler realized it's a CPU oriented job, so it should be, I mean, we should behave something separately with, for the other jobs which are actually IO oriented jobs, right? So, for example, if some job is IO oriented, it's always good to schedule them as early as possible because they need some interaction with the user, maybe, right? So from the user perspective, if you want to minimize the responsiveness, right, then it is always good to schedule them as early as possible for the IO oriented job. So you should consider them separately, right? So how to predict such thing unless and until you see their past behavior, right? So here basically multi-level feedback queue, what we are going to do, so it maintain a list of priority queue. Okay. And initially all the jobs whatever you have, so you give all of them in the same priority, let's say highest priority. Okay, right? So as I mentioned, so there would be several priority queue, several queue with different priorities, right? So of course now if you have uh, a job which is in higher priority, right, so that job should be scheduled first by your algorithm, right? And if some job is actually with respect to the same priority level, right, then they should be also treated fairly, right? So what the feedback, multi-level feedback algorithm will do, it will consider all the jobs in the same queue, same priority queue, and they will run round robin. Okay. And if they are in this different queue, then just depending upon the priority, it will schedule them. Okay. So in other words, so you have actually mainly two rules. Let's say I have many jobs. So if you so in the multi-level feedback queue, you have, let's say, since this is a policy, right? So you must have some rule. So the first rule is something like this. Let's say if you have a priority of a job is bigger than the priority of another job, so you should run the job with the higher priority first. Okay, so that's the first rule. Okay, and the second rule, as I mentioned already, if they are in the same priority, then you should run in a round robin fashion. Okay, does that make sense? So we have, let's say, these are my first two rules, and we'll introduce more rules, of course, one after another. So after understanding the situation. Okay. 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 So now the question is, since as I already mentioned, so this multi-level feedback queue is actually behaving something like this. So you have the history. You are maintaining the past history or past how the job behaved in past, right? So that history you are maintaining somehow, right? So of course you should, in ideal situation, you should change the priority of some job, right? Depending upon its behavior, right? It should not be, the priority should not be stagnant for all the jobs all the time, right? It should vary, right? Okay. Now the question is when you should vary, when you should change the priority of a job. Okay, that also you need to decide, right? So what do you think when I should change the priority of a job? Let's say it was in the highest priority, as I said, when the job came. So it was actually in the highest priority level because we don't know the behavior of the job, right? But with respect to time, we realize that, okay, it should not be given in the highest priority. I should change it. It changes priority means I should change, let's say, as I mentioned. So here basically you have many queues, right? Let's say this is the highest priority and this is the second priority, third priority. I might have k many queues, and this is the lowest one. Okay, so when the job came, so it was in this priority, so it was immediately scheduled, right? I might have several other jobs keep coming, right? And I will just add them in that queue. Okay, But at some point I need to actually decide that okay, some of the job over here I should move them from there to uh, the next priority level, right? So what should be that point? Do you have any idea?
IO-bound, IO-bound,
Yes. Huh?
IO jobs
Akshay?
should be kept at high priority because they give us spaces between two successive time intervals. So at that interval, we can schedule another job. So the point is, if
Uh,
job is IO bound, give it high priority.
Ah,
You
right,
will
right,
able
right,
to
right. But right. So how will you understand? Because see, there is no way to. So you need to, if you want to implement some policy. So we don't know a priori, right? That this job is going to be IO oriented job. This job is going to be CPU oriented job. So how would you understand that? Right? So the only way to know this, let's say, as I mentioned, that in that priority, in the same priority, if some jobs are there, right, many jobs are there, we are actually going to run the round robin, right? So there is some time slice, right? So let's do something like that. It might happen that we don't know which of the jobs are IO oriented, but if we see, we had the time slice and before the time slice was completed, some of the job is actually relinquishes the CPU. It is actually giving up the CPU. Okay, and it is going for IO. Then you realize, okay, it was not utilized. It has not utilized that full time slice. It actually went for IO in the mid. So we should keep that job in the highest priority, right? We should not move right now immediately to the lower one. But if some job has utilized its time slice, then we should remove it from that to the next level. Realizing, okay, this is going to be CPU oriented job. Let's make it because okay, with respect to response time, we don't need to bother right now. So that could be one rule. So that's exactly the situation is, right? Okay, I have. So this is just for example. All right. So let's introduce more rules. Okay, incorporating this changing of priorities as we mentioned. So for example, let's introduce rule 3. So rule 3 is so we know rule 1 and 2. Do you remember the rule 1 and 2? So because we need to remember these rules because these are the policies and which will enable you to build up your algorithm. Okay, so you need to remember these policies. These are the first two rules. Okay, now let's implement the third rule. So what is the third rule? So third rule is, as I said already, if a job enters in the system, it is placed at the highest priority. Okay, that's my third rule. And let us have another two rules which we are actually defining at 4A and 4B. So which says something like this: if a job uses an entire time slice while running its priority, so it might be, so let's say the job is running in this priority, or it might happen that the job was running in this priority level and the time slice was this, and if we see that it has utilized this whole time slice, so I will move that job from that priority to next level of priority, lower priority. Okay, that's my rule 4A. Okay, and if we see if some job gives up the CPU before the time slice is up, so then that job will stay in the same priority level. Okay, so let us introduce these rules. So now we have basically 5 rules, right? 4A and 4B and other 3 rules, right? So in this manner, if you are going to implement, then basically MLFQ will behave almost like shortest job first, right? You can see one example. For example, let's say let's say I have just one job. Okay, if I have just one job, you can see it was first in this. This was the highest priority. Okay, for me it was P1 was the highest priority, but here this is the highest priority. Okay, it was scheduled. Then there was no other job in its queue. So and it has already used its full time slice, so it is moved to the second queue, right? The next level of priority queue, and we are running this job. Again, there is no other job, so there is no question of round robin here. But we are making this job to the next level of priority. and this is, let's say that this is the last priority. Okay, this is the last level of priority queue, and we are continuing, right? Since there is no other job, you are continuing and finishing this, right? So far, if you just implement these rules, then with respect to this one job, it would behave like this. Is the picture clear to all of you? Is the picture clear to all of you? So it's very simple, right? Okay, now let us see another example. So here basically I have again two jobs mainly. The job A is basically CPU oriented job, CPU intensive job, and the job B it is actually IO interactive job. Okay, and this is the color corresponding to them, and this is the highest level. Okay, so in the highest level, okay. So basically, okay. So A was actually so right. So A is this same job. Okay. So it was here. Okay. Now the second job came. Let's say that job is B. Right. The moment it will come. So the moment it will come. Let's say the job B came at this moment. Right. So the job A was running in the lowest priority level. For example, in this way, if you just run it, right, it will run in the lowest priority level. And let's say at this moment the job B came. So the moment the job B came, so that job will actually got prioritized, highest prioritized, and it will get chance, right? And in this slice, maybe if he has completely utilized, right, then it was moved to here, and it will finish, right? Its job. If it is a small job like that, okay. And if you have IO, then the picture would look like something. So here there was no IO. The job B was of length just this much, okay. And it was actually you can see. So it actually behaved like shortest job first, with preemption. So STCF, right? STCF, okay, right. So it is exactly same with respect to shortest job first, right? So this is the moment when the smaller job came, so it got prioritized, it got executed fully, then the bigger job got the chance, right? Okay, now if you have IO in the picture, then the picture would look like this, okay. For example, the job B is now highest priority, okay, and so what it is doing, it is actually, so can you see the picture? So here basically, so the job was very small. I mean, so after utilizing very small amount of it actually did not utilize its full time slice, right? And it relinquishes the CPU, right? So at this moment, since it was actually relinquished, the CPU was free. So at this moment basically, this corresponds to this moment. The job in the lowest priority got chance. Okay, it was scheduled. And when it will come back, then again it will get chance. Then again this job, since this job B is IO oriented, it relinquishes the CPU. Okay, it gives up the CPU, and that moment means this is that moment when it relinquishes the CPU. This moment the other job gets chance. Okay, so you can see, I mean how the situation is. It looks like, okay. Now, I hope you have understood, right, all the policies with respect to the MLFQ, which we have introduced so far. Now, I have one question. Okay, I have one question. So, can you see some problem with respect to this basic MLFQ? Means, let's say I have only these 4 rules, 4A, and with respect to 4A and 4B, means let's say 5 rules in our hand. Then, can you see some problem?
Ma'am,
Do you see?
I have a question. In case yes, ma'am.
So, yeah.
So in case of job A, when the job is in the lead priority, so what we were doing was we were letting the job complete on its own. There was no concept of time side at that time, right? Because in the previous page, can you turn up? Can you go to the previous page?
Right here,
Yeah.
no?
Yeah. So we were allowing the job to complete on its own, right? This was one.
Okay,
But,
right. So if,
but
no, mhm,
so in the next slide, what
mhm,
is happening that what after whatever time it is, whatever time slide that you mentioned in the
mhm,
2020 queue, so it is
mhm.
automatically relinquishing CPU and the CPU usage is being passed on to job B. So how is it so? How is it happening? Why is it not completing? And why is it that the CPU is being transferred to job B in Q2?
Okay, so if I understood your question correctly, so you are saying, so how this relinquishes happen, right, automatically? So even the in here, right, in this queue, you are not completing the job, right? You are saying
Exactly.
that relinquish. Okay, so that's a good question. So right. So if you remember in the last class, we discussed about context switches between the processes, right?
Yes.
So whenever some job is going to have some IO and it will come back, so it will actually give there's one interrupt, right? To that interrupt will be taken care by the scheduler. So it means the scheduler will now it now knows that okay, this job is now ready. So we need to schedule that job, and we know that it was in the this highest priority queue, right? So we need to actually schedule that job. We should not continue with respect to the job A. We should give chance the other job, means the job B should get chance, right? Does it answer your question,
Yes.
Akshay?
Yes.
Okay, good. So in this way, actually, this interaction, so interaction is happening means, I mean, the charge, operating system is actually getting charge of this. It is responsible to take care which job should get chance, right? By this interrupter. Okay, with the help of interrupter. Okay. Okay, that's good. But I have one question. If you understand this policy so far, so my question uh, is there any problem? Can you see something? I mean, or so far, okay, so good. This MLFQ, whatever we have, the policies, it is okay with us. Is it okay? Can you see some problem? Okay, maybe okay. I will give you some hint. Can you see that uh, someone may, if somebody knows, so what is the time slice of the highest priority? So it might happen that I can game the system. Means if I know that okay, this is this much amount of time it is going to be occupied by the I mean this is the time slice of the highest priority queue, right? And if we know this a priori, let's say, then I'll write one program which will actually will take that less amount of time compared to that time slice, and before completion of that time slice, it is going to invoke some system call. Maybe it is just self-blocking system call, okay, and it will come back when it needs, right? So that it can actually maintain that I will be in the highest priority, right? So it in other sense, there one gamer can be actually there, so who can actually just fool the system, right? So that's the problem so far which we have discussed. So this is one problem, but there are other problems also. For example, starvation is another problem, big problem. For example, if you see this picture, right? So this is a CPU oriented job, right? So this job, though this job came very early, right? For example, let's say it came here, then okay, it was going on, then this job came, right? Then so, but it might happen there are smaller job keep coming on, and since this job which was actually got scheduled earlier, which came earlier, and the scheduler actually made its priority the lowest, right? So it will hardly get the chance, right? So if all the smaller jobs keep coming, so there will be starvation, right? Can you see this? It's a big problem. So starvation is a very big problem with respect to the current situation, whatever we have. So we need to come out of this. We need to come out of this starvation, right? There should not be starvation like this. Okay, this is one problem. Another problem is, as I mentioned, game. You can actually fool the system, right? After running 99% of the time slice of the highest priority level, You just go for IO, or maybe just block you. I mean, block. You just invoke the block system call, which will block yourself, right? And you, so you keep gaining the highest priority, right? So this is another problem, right? And a third problem is we also did not incorporate. So that another interesting issue is this is actually issue. So we did not incorporate something like this. So for example, we said that okay, we have realized that this job, for example, this big job, it was actually, if you remember, it was running in the highest priority level when it came, and we actually thought that it is a CPU oriented job because it utilized its full time slice, right? So, but it might happen later on. It is interactive job, right? So, and it is in the last priority, lowest priority level, right? So that's another problem. So these are the three problems so far we have in the system with respect to the rules which we made, right? So if you want to build your system, then as I mentioned, I mean, you should have a rule, right? Some fixed set of rules if you want to make some policy. So with respect to the current rules, these are the problems, right? We should come out of the situation. Means we need to modify our existing rules, or maybe we should add some new rules. Okay, can you guess, or can you, I mean, uh, can you tell me some rule change, or maybe some kind of new rule which we should incorporate in this scenario so that we can come out of these problems? For example, let's say we want to come out of this third problem. So how to come out of this? Any idea? How
Ma'am,
to
I
come out
had
of?
a doubt.
Mhm, mhm,
So, for,
mhm,
so whenever we are running some code,
mhm,
uh,
mhm.
so running that code is like invoking a process. So is first that code has to be compiled
You
and then
compile it. Yeah, then you are running, right?
executable is
Mhm,
formed.
mhm, mhm.
So is the compilation and execution two different processes, or such that the compilation is a parent of the execution process, or are they the
No,
same?
no, 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 no. They're different. Compiler is, so have you heard about compiler? So compiler is different. So which will actually take your program and it will just build, it will compile it, right, and make the executable. Okay, and
So
execute. Right.
is it
Yes.
when we are compiling, is it
Uh,
possible for us to like record input
which
output,
record means? What
as
kind
in
of?
like not, is it possible to like
Uh,
figure out if there are, because compilers go through the syntax, right? So
hmm,
is it possible to like identify how many input output operations we have,
how many input? Okay.
statically? Yeah.
Okay, so basically the compiler will just compile the code and it will make the low level executable, right? So if you want to keep track of that information, right, now you want to inform the scheduler, right? Is that what you want to do, if I understood it correctly? That beforehand
Yeah.
you want to, but we
Yeah.
don't know. So if you remember the program and executable, right? So it depending upon the input, right, it might take several different paths of execution. So you can't have. I mean, you might have three times you might write the IO operation, but when you are going to execute it, we don't know, right, how many times it is going to be executed, right? That path we don't know how, in which path it is going to execute,
Yeah.
unless and until you execute it, right? It's something which you are talking about, whether the program is halting or not, something like that, right? So we don't know. This answer is, I mean, the compiler, though, it can't judge how many times it will be executed. Some IO is going to be done. It can just see, okay, some IO is there, that it can see, but
Yeah.
even it can't decide, okay, or whether that IO is going to be executed if you are going to run your code, right?
Yeah. Okay. Okay.
Right. Okay, good. Good. Now the question is, if you understand, so let's say I want to stop. First of all, one by one, we will stop all this bad behavior, right? So first, let's say we want to stop this scenario. Starvation, we want to stop. Let's say. How will you stop starvation? Okay, can you tell me what should be the which kind of new rule we should introduce in the picture so that starvation will not be there? Means, uh, I hope you have understood starvation, right?
Reset the queue.
Reset the queue, right? That's the good option. So when you are going to reset it, right? Right. Good option. So yes, so basically reset the queue. That's the option. Basically, you need to boost your priority, right? After some interval, let's say that interval is S. What you can do, you move all the jobs in the system to the topmost queue. Okay, that's my new rule which we are introducing to stop starvation. So if you are going to introduce this, then basically after some interval of time, so this big job will not start there, okay, in the lowest priority level. It will be moved. In fact, not only this, all the jobs in your system will be moved to the highest priority level. Okay, so that's our new system, new route which will stop starvation. But okay, if you are going to make that rule, how about this third situation? Is it also automatically, this is also handled, right? If you are going to, this is also handled. This rule, fifth rule, which we just designed, it is also handling this situation. Since we thought that one job is CPU bounded, but later on it might happen that it is actually IO bounded. We don't know it. So after some interval, right, this S amount of time, you are moving all of the jobs in the highest priority level. So fairly, you are thinking that okay, they are as if they have started from the beginning. We don't know their status, whether they are IO bounded or CPU bounded, right? So you are taking care of this also. Good. Now the only question or only bad situation which you have is actually gaming the scheduler. Means you are fooling the scheduler that you could not stop by by introducing this new rule. So can you think about something, some new rule, or maybe you need to modify existing rules so that starvation is not there? Okay, first let us see what are the, yes, any answer? First let us see how many rules we have so far. So I hope you have remembered rule number 1 and 2. Rule number 1 and 2 was basically, it was saying if priority is bigger than some job, then the highest priority job will be run first, and if they are in the same priority, then they will be in the they will be run in round robin fashion. That was the two. Those were the two rules. And third rule says that if job comes for the first time, so it will be scheduled in the highest priority level, right? And rule 4A and 4B says if some job utilizes its whole time slice, then it will be moved to the next priority level, right, lower priority. And if it relinquishes the CPU before utilizing the time slice, it will be kept in the same priority level. So basically, this rule is actually stopping you. This rule is very specific. Rule number this 4B. It is the rule which is responsible for fooling the system. Means gaming is easy because you have, gaming is happening because you have this rule number 4B is in the picture. So you need to actually modify this rule. Okay, so can you suggest some modification? You need to see, right, what are the existing rules, which are the problems. So in this way actually everything will happen. Even if you are going to make some new system for somewhere, right, this way you need to consider and you need to think. Okay, so you need to go back the existing, see the existing policy, and you just see which of the policies are culprit. You see that and you just modify it. Okay, so here this one is the culprit, so you are going to modify it. Can you say? Can you tell us something, some idea maybe? Can you give so that if you modify this rule 4, right, and if you just add something, modify this, update this rule 4 some way, then it will stop gamer to game the scheduler. I hope you have remembered, at least you have understood what is the gaming we have mentioned. Do you understand? Okay, let us see. So it's very, uh, straightforward, right? So the rule is something like this. What I am going to, I am just modifying the rule 4A and 4B, and this will be my new rule 4. Okay, it's not rule 5, it's rule 4. So what is that? So we are saying Okay, once a job uses up its time allotment, total time allotment, let's say it was a time slice we are talking about, right? So even if it relinquishes the CPU and it will come back, right, at some point of time, and we are saying that if you use that the time equivalent to one time slice, right, in total in that priority level, then you should move that job to the next level. You should not run it. So in this way, if you are just maintaining, then basically this will not happen. That gaming will not happen. Okay, gaming of the scheduler will not happen. So that's the thing. Basically, we modified the rule 4A and 4B, and the modified rule 4 is something like this: once a job uses up its total time allotment at a given level, regardless of how many times you have used it, its priority is reduced. Okay, it is moved to the next down the queue. Okay, okay.
And what
So
is the difference between total time allotment and time slice?
say that once again.
What is
Chacha, you are
yeah, difference between time allotment and time slice? What is the
time size. Okay, okay. So here basically, okay, time allotment means it's that time slice itself. Okay. So for example, if you see this picture, the previous picture. Okay, just a minute. If I have better picture, I'll see here. Okay, is it a long job? This is not right. Okay, good. The picture is something like this. If you see here, right? So this job, maybe the time slice was something just bigger than this amount, right? So that's a time slice it has not used, right? Utilized it. Okay. So now you just sum up this time and the next time whatever you are going to use. So if that amount of time is bigger than one time slice, okay, that is the time allotment. Let's say they are same actually. If that is bigger than the time slice, then you are going to lower down the priority of that job, and you are making sure that that job is moved to the next priority level. Okay, does it answer Akshay your question?
yes, sir.
Okay, good. Okay, so basically now now you can see the picture basically here. In the left you have uh, you don't have okay, right, it actually here you don't have gaming okay, no, left is actually left without left, okay, and with right gaming tolerance. Okay, right. So this is basically where you don't have, you have the gaming tolerance, means you have introduced the modified rule 4. Okay, rule number 4 is there, and here you don't have the rule 4. Okay, so you can see this job is actually fooling you all the time. But if you consider with respect to the new rule, right, new rule to specific rule number 4, modified rule, then it will be automatically moved to the next priority level, right, once it uses more than the time slice. Okay, move from here to there again. So it will, so you can see after this much of interval, it is actually evoking that it is going for IO, right, after that much amount of time. So here basically in the for the first time, maybe it has used it full time, it will be moved automatically. Next time onward, it is here, it is going to use. So even after, so in this small gap, the lower priority job will get chance, right? Next time it will come here, and if you just add this whole amount of uses, it is actually equivalent to one time slice, right? So now basically this job is scheduled to the next lower priority level. Okay, and the picture would looks like this. Okay. And if you don't have this tolerance, means with respect to the old rule number 4, so the picture would look like this. It will be always here. Okay, and the jobs over here, they will actually start. Does it make sense to you right now? Okay, there are other more examples. Again, here basically you have the tolerance, means you have the new rules, and this is with respect to the old rule. Okay, right? Okay. Okay. Right. Now, if you understood the MLFQ, now there are several design parameters left out which we did not discuss so far. So one of the thing is, if you remember, we said after some S time, amount of time, we are moving all of the jobs in the highest priority level, right? Now the question is, what should be that time? S should be how much big? That is again design decision. Another question is, for each of the priority level, there is a time slice, right? For each of the priority level, right, in the queue. Again, what is that time slice? What should be the time slice for each of the level, right? These are the design question, right? If you know already what kind of system, what kind of environment is there, what is the workload of your system, right? Then maybe it is easier to you to decide what should be the time slice for each priority level and what would be the size of S, right? Can you tell me at least if let's say I am going to have the time slice that S, that capital S is very small, let's say, then what would be your problem or what advantage you have? Can you tell me?
Can you repeat it?
So I hope you have understood the big time period S, after
Yes.
which interval we are actually moving all the jobs with respect to, I mean, wherever it is, I mean, we are just moving it to the highest priority level after certain amount of time, that S amount of time. Question is, what would happen, I mean, if I make the value of S very small, or what would happen if I make the value of S very large?
If S is too
What?
small, starvation would happen because all the processes will be in the top priority.
If S is big,
Too small.
then if, right? If S is big, then starvation will be more, right? If S is small, then what would be the problem? Very small.
No, no, I didn't get it. I said that if S is small, then starvation would happen. I didn't get the idea if S is big, then starvation would happen.
If S is small, then how the starvation will happen?
No, because if S
Huh.
is small, you will anyway move all the jobs in the topmost priority.
Highest.
So
Right.
for the entire
Huh.
time, all the
Huh.
jobs remain in the topmost priority. So all of them
So
use the CPU all the time.
right, but they will be in round robin fashion. In round robin fashion, there is no starvation, right?
Yeah,
All
yeah,
of them will get chance, right?
yes, yes.
So if it is get stuck in the lower priority level for a long time and small jobs keep coming in the highest priority level, then your job in the lowest priority will starve for a long, right? So see, if you make your S very big, right, it's a very, after a very long amount of time you are doing this boost up thing, then basically starvation will be there for a long time. But if your S is small, right, then starvation will be less, right? Less amount of time it will be starved. But if your S is small, there is one disadvantage. Can you see this? If S is small, there is one disadvantage. Then basically overhead is there, right? You need to move all the jobs irrespective of where it was there, right? Okay, I think we are running out of time. Then we are moving them to the highest priority level. So this operation, it's a operating system needs to tackle, right? And this is a overhead. If you are going to do this very frequently, this operation, it's overhead. Okay, very good. I hope you have understood the MLFQ. So, in summary, I have these 5 rules. We have these 5 rules. So, rule number 1, 2, this is nothing to say. Rule number 3 also is nothing. This rule number 4 is the main thing. So, and rule number 5, it is actually for to remove the starvation, right? In a nutshell, these are the 5 rules. And if you understood this carefully, so now I had only one question left. So what should you have the time slice? What do you think? So highest priority time slice बड़ा होना चाहिए और छोटा होना चाहिए. So what do you think? Time slice of the highest priority should be larger compared to the time slice of the lower priority, or the other way? That's my last question. If you understood
It should be
huh,
smaller, I
yeah.
guess.
Right. So in the highest priority level, you are assuming that they are actually IO oriented, right? So it should be the case that in the highest priority, the time slice should be small, right? And if you as you go down the line, the time slice should be bigger. But the question is how much bigger it should be. That's a design decision. And actually, this MLFQ is implemented in some of the system, and sometime there are actually option for the user. Actually user also can say that okay, user or in fact administrator, they can decide what should be the priority. Okay, in huge priority should be okay, that kind of, or maybe how much time, right? That should be there. That type of design decision should be there. Otherwise, let's say I have just implemented one operating system and I have fixed this time slice is everything I have fixed. Then we don't, and we have just sent, I mean, just release that operating system, right? And if it is the case, we don't know where it is going to be used, right? In which scenario, and then either you will be it will be more overhead, or maybe it's what should I say? It's a starvation would be there, right? So what should be the exact value which will fit into your environment? There should be some flexibility also, right? So that user can also decide, or user in the sense administrator. Okay. So that kind of flexibility is also there. In fact, there is, if you used some command prompt, if you use, have you ever used some command called nice? Using this, basically you can change the priority of some of the process. Okay. So that kind of thing is there actually in the system. Okay. Okay, with this, I think we have all the things in a nutshell for scheduling. So we have seen the best scheduler possible. I mean, at least, I mean, in our hand, MLFQ, which is very beautiful scheduler, I would say, which takes into account the past, right? And depending upon the past behavior of a process, it predicts its future, right? And it tries to minimize, of course, you can see that with respect to response time, it behaves very nicely. With respect to turnaround time also, it is better than round robin, right? Okay, very good. With this, I think I should conclude today's session. If you have questions, you can ask. Please feel free to ask. Okay. Do you have any question in your mind? Okay, if not, so I hope the first lab assignment is released and you are working over there. Okay, and I hope you're also active in Piazza. Our TA Neil, he is very active with respect to that. If you have some questions and all, you can discuss over there. Okay, please feel free. So though I am not active in Piazza, but you can go ahead because I hope Neil is active. But if you have some specific question, just pass to Neil. I'll try to answer it. Okay. Do you have any other questions? Any questions? If not, do you have any questions? If not, okay, let's conclude today's session. Bye. Take care. Okay. See you next Friday. Okay. Okay. Bye.